One of the important class of systems that we will study in this course is the class of linear systems. So let's talk a little bit about what it means for a system to be a linear system, or what linearity of a system means. Now suppose we have a system which I'm going to represent by H, and we have a certain input signal to this system. Let's call it input of t, which produces an output signal, output of t. Particularly when the input is x1 of t, let's say the output from the system is y1 of t. We say that a system is linear if it satisfies two properties. Okay, the first one is what is known as additivity or superposition property. So the superposition property essentially says the following. It says that if the input x1 produces the output y1 and the input x2 produces the output y2, then if the sum of the input signals, so if I consider a third input, let's call it x3 of t, which is actually the sum of x1 of t and x2 of t. If the output corresponding to x3 turns out to be equal to y1 plus y2, then we say that the system satisfies the superposition property. Okay. Now what I mean by that is, in general, if I consider an input x3 of t, which is x1 of t plus x2 of t, I will get some output, and let me call that output as y3 of t. But there is no guarantee that y3 of t is actually equal to y1 of t plus y2 of t. Only when the system is linear, or only when the system satisfies the superposition property, is this true for all values of inputs x1 and x2. Okay, so that's really the definition of a system that satisfies the superposition property. So we can look at a few examples of let's look at a few examples of systems that satisfy the superposition property, and examples of systems that do not satisfy the superposition property. Okay, so suppose I have a system, let us say y of t is t times x of t. And like I said in class, or perhaps in one of my earlier lectures, I think it's always better to think of a system in terms of something like this: output of t is t times input of t. Because a lot of times we will use input signals which are x1, x2, so on and so forth, and it's kind of easy to get confused between the fact that x of t sometimes represents the a general input versus a specific input we are talking about for a particular problem. So I kind of like to think of it as the output at time t is t times the input at time t. Okay, now the question is this system or does this system satisfy the superposition property? Well, what do we have to do to figure that out? Suppose I consider an input x1 of t. I know that my output y1 of t is going to be t times x1 of t, because I'm just going to apply this relationship to the input x1 of t. Okay, now if I use this relationship to find the output corresponding to x2 of t, I'm going to get y2 of t is t times x2 of t. Now what I want to do is to consider a third input x3 of t, which is equal to x1 of t plus x2 of t. Now this input-output relationship for the system tells me that the output y3 of t is going to be t times x3 of t, but x3 of t is t times x1 of t plus x2 of t. Okay, now the system satisfies the superposition property if y3 of t turns out to be the sum of y1 of t and y2 of t. Okay, the question is this true? And in this case, it's fairly easy to see that it is true, because we can use the fact that multiplication distributes over addition, and then rewrite this as t times x1 of t plus t times x2 of t. But this is nothing but y1 of t, and this is nothing but y2 of t. And so the system satisfies the additive property. Okay, so the system satisfies the additive or the superposition property. Okay, now there are examples where this is not true, and let's look at one of these examples where it's not true. I mean, it's kind of easy to come up with the in fact, I would urge you to stop the video here and try to come up with your own example for a system that would not satisfy this property, right? Maybe it's easy to come up with the examples like y of t is equal to x squared of t, for example. Okay, in this case, you can see that adding x1 of t plus x2 of t is going to result in the square of x1 plus x2, which is not just the sum of x1 squared plus x2 squared. Okay, so clearly this is not going to be an additive system. Okay, so here is another example. Say we have y of t is x of t times x of t minus 1. Okay, so you can think of this as output of t is input of t times input of t minus 1. Okay, now if I consider an input x1, my output corresponding to the input, maybe I will write it. So x1 of t will result in a signal y1, which is x1 of t times x1 of t minus 1. And x2 of t results in a signal which is y2 of t is x2 of t times x2 of t minus 1. And if I consider a new signal x3 of t, this is x1 of t plus x2 of t. So what I will get at the output is y3 of t, which is x3 of t times x3 of t minus 1, which is x1 of t plus x2 of t times x1 of t minus 1 plus x2 of t minus 1. Now you can see here that when I multiply these out, I will get x1 of t times x1 of t minus 1 plus x2 of t times x2 of t minus 1. But I also get the cross terms, which don't actually go away. Right? So this part is actually y1, this part is actually y2, but I end up with something more. And so y3 of t is not equal to y1 of t plus y2 of t. So it does not satisfy the superposition property in this case. Okay? All right. So remember, we were talking about linear systems. A system is said to be linear if it satisfies the superposition property and another property called the homogeneity property. We say a system is homogeneous if a scaling of the input by a constant scales the output by the exact same constant. Or what I mean is, if the input x1 of t produces y1 of t, and a times x1 of t, where a is just some constant, produces a times y1 of t. And this has to be true for all x1 and all a. All constants a and input signals x1 of t. Then we say that the system is homogeneous. Okay. As examples, you can see that you can verify that the system that we considered first, namely the system y of t is t times x of t, is in fact homogeneous. Whereas the second system, y of t is x of t squared, is not homogeneous. Now, you should be a little bit careful here, because in the second system, if I scale the input, the output also gets scaled, but it gets scaled by a squared instead of getting scaled by a. So the scaling factor has to be exactly the same for the output. So this is not homogeneous. Okay? So a system is said to be linear if it is both homogeneous and additive. A system is linear if it is both additive and homogeneous. A system is said to be nonlinear if it's either not additive or not homogeneous. Okay? Linear systems are very prevalent. A lot of systems in practice are modeled as linear systems, and there are a lot of mathematical tools that are available for us to analyze linear systems. By contrast, analyzing nonlinear systems is substantially harder, and in fact, it's nonlinear is just too broad of a classification as well, because I mean there are a lot of systems that are nonlinear, and there are very few general tools that apply to a lot of nonlinear systems. Whereas for linear systems, there are a lot of mathematical tools that can be used to analyze linear systems. Okay, so this is why linear systems were a very important class.